We have a proper restart. Oh, yeah. Everything started running properly. Sorry, Arnold. I came.
It's not a type 1 typo where the
Welcome everyone for Arnold's Part 2 seminar, picking up from where we left off 2 weeks ago. And while I'm up here, I'll also acknowledge the traditional owners of the land that we're meeting on today, particularly during Reconciliation Week. Pay my respects to their elders, past and present. Thanks, Arnold.
Okay, today we start part 2. Just quickly review what happened 2 weeks ago. The right-hand side just show you how we do the sort of like a filtering process. We need to find out the upper and the lower string envelope functions, and we find the mean for those two functions, and then remove it, and then we got the residual. That's how we do the EEMD. And we try to get the mean of the both envelope function as close to the 0 as possible, and that's based on the Hilbert transform theory. And the last time Siobhan also asked, like, say, when you decompose the signal, what's the percentage, compared to the original? Like, in UF, we will ask, like, what's the eigenvalue, like, how many percentage you describe your original function. In here, you just do the standard deviation of the outcomes and then divide by the original data. And then that percentage, that will just tell you how much that means for the whole component. The third and fourth, Siobhan also mentioned, but emphasize these two, but actually I don't really want to show that, because I think it's too much equations here. But anyway, The main difference between FFT and then the EEMD is because under the FFT, both amplitude and the frequency are fixed. So one frequency, one amplitude is a pair. Yeah, it won't be changed. But under the EEMD, amplitude is a function of time, and omega is also a function of time. That's a major difference when we use the EEMD. Okay, today we move on to another more details I want to emphasize again. Is so-called the nonlinear multiplicative process. In the real world, most of signal what we get, like in the model, in the observations, most times a nonlinear multiplicative process. It's either through the amplitude modulation or through the frequency modulations. So like say, if you look at the Fei Jing's famous conceptual model, you can see the red color words that show actually that's using the amplitude modulation. Somehow, yeah, the emission is not working, but anyway. And the other thing is at the bottom, the C mode. That's what Fei recently introduced. So he used whatever the signal multiplied by cosine to represent as atmosphere noise, and he called this as a sinc function. But from here, actually you can see this is also a amplitude modulation. So when you do the amplitude modulations, you can see the amplitude of the function will change. So you can see the amplitude of the signal is up and down. It's rather than like pure noise anymore. Pure noise is very flat, but once you modulate together, the amplitude becomes your signal's amplitude. This is very important because I won't talk in this time, but we'll use this one in the Amos talk later to describe to figure out what happened to the Westerl events. Okay. What I'm going to talk today is last time we talked about the one dimension, but this time we talk about the multi-dimension. That was from Zhao Wu. He's the one to invent this method, and Ho and Lee is the one to to apply that equation into the MATLAB script. And myself and using that MATLAB script convert into the NCL, and this is free to download. You can use it. At this stage, in the Python version, I haven't finished yet. Only finished one dimension, 2 and 3 dimension not yet. You can use the EEMD on NCL now, but be very careful. Under the NCL, that's only for one dimension or single dimension only. You can't use it for multi-dimension. You have to use my script to call the NCL function, and then you can do the multi-dimensions decompositions. The reason why I want to introduce these 2 seminars because a lot of people start to use EEMD in the climate research. Particularly like some people didn't realize we can use EEMD as in 2 dimensions or even in 3 dimensions. So why we have to emphasize like this? Say like if we have a SST anomaly on the left-hand side, if you pick out say the green box and then the yellow box, and then you decompose it, you can get the IMF 1, 2, 3, 4, 5. And the higher IMF or the residual usually represent as a trend. And then there's a paper just say, okay, now I say IMF 5 in anywhere else represents as a trend, but actually it's not right because as you can see, the right-hand, the green box and then the yellow box is at a really different place. So in each place, they may contain a lot of different message. So say like the one close to Australia, that one we may maybe influenced by the Australian monsoon, Asia monsoon, Indian monsoon. And then on the right-hand side, the green box may be only like El Nino or something locally local to the American that side. So maybe we'll have less information or less noise there. So you cannot just like apply EOF at anywhere else and then say I'm fine in every place are the same. No, you cannot do that. You have to decompose it, not only the time, you have to decompose it, the space as well. I'll talk about more details after this. Okay, what is the MEMD? I just call it like a face-off. It's based on EMD and based on EMD. You will take off, this is like a face-off. You will take off your skin, your scalp, your muscle skin, or muscle layer, or nerve system. So it's like layer by layer. It won't mix up everything. So say if we have a SCT anomaly on December 2015, as we know that's an El Nino year. So the left-hand side, that's just SCT anomaly. Well, we saw that almost every day, every time. But what's the message embedded in this 2D signal? We apply the multi-dimensions EMD, and then we can decompose into this A mode in space. First two modes is really like a noise. 3, 4, 5, 6 EOF is more like the signal, what we want. 7 and 8 more. 7 is like a residual, and the 8 is very funny thing. 8 actually is the surface trend. Okay, when we do the anomaly, we will remove the annual mean, but that's on the time spec rather than the space spec. So we even remove the time spec, the mean, but we didn't remove the space mean. So that's why in here that will show you there's a little trend on the space. So that means north and south, there's a trend always there. But yeah.
Only have one field. The field only one left field of one time.
Yes.
How can you see a trend? Trend is time. You don't have a
Space trend. Here is higher than you because even it should be supposed to be winter in the northern hemisphere, but you show there's a warming. Why? Because I remove like 30 years average of December. I only remove the timing, but I didn't remove the space mean. Yeah. So somehow in December in this time we still have quite big residual. This is something like somehow I think no one saw this before. And when my first time to have this one, I just, something wrong with this function. How come, I got this so big? Because it's like 1 degree, can go up to 2 degrees. And then I'm being asked like, what's going on? And I just realized, when we calculate the climatology and then remove the climatology, that's more on the time base rather than the space. So in here, we're talking about more in space. So we are really focused on 3, 4, 5, 6. It's more something like a El Nino. But before that, last time in the group meeting they didn't talk about this, but this time we'll talk about more details. How did I do this? Okay, so if we have on the left hand side we have original signal. That's in the gray box. So we have the I1 to I4, J1 to J4, like 16 dots, or 16 grids. So how we do apply the EMD? First, we apply horizontal. So we decompose it only the horizontal way. So the green box will represent as high frequency, and then slightly higher. No, low frequency. Until the red ones, that's the low frequency. Yep. Yeah, you should come to the last talk. Yeah, no. Okay, I go back. Yes. Okay. Yingping just asked, how did I choose the frequency? This is EMD. This problem is also the suite of EMD. We don't choose, we don't define the frequency. we say like in here, it's very simple. If we have a signal like in the gray curve, we have you can see this high frequency and low frequency embedded. How can we separate? We don't set up like a FFT. We say like from 2 day to 5 day or 5 day to 100 day something. No, we don't do that. We plot upper and the lower envelope functions as the green and then the orange ones, and we take the mean of these two functions. In this case, that will fit to the green curve, and then we remove that mean of the two envelope functions, and then the residual will be the first mode of the IMF. So if we have more signal here, we keep doing that, and then we will have a lot of frequency. So in the space, we also can do like that. We have a very curvy surface, like say in ocean, we have different wave. We just also apply the envelope functions and then remove that. And the residual, first residual will be the high frequency, and then second high, and then become like a low frequency. That's why we do that in the space as well. So that's how we do that. We apply on the space. And so at this stage, we only focus on the I dimensions, so only horizontal. And then we got the high frequency as the green, and then the low frequency as the red. That's only one dimension. And then second, we're going to do the vertical, the J directions. So from that 4 box, we do the vertical dimensions. The green, we do and then the orange, the blue, and then the red. We also do that. So that 4 component, we do the vertical decompositions. Can follow that at this stage? It's independent. Yeah, there's no criteria for orthogonal, but it's close to be orthogonal, yeah, like 0.0001 something, the correlation. Yeah, so that's the way we do the 2D dimensions decomposition. Okay, and the last ones, because we can see the outbound actually is more in high frequency stuff. We just put them together as the final green box on the right-hand side. And then follow that, we have this inner bounds, and then the last one, that will be the residual as the high frequency on the red box. So low frequency, yeah, sorry, low frequency as the red box. So from previously we have that 16 grids, and then we decompose it into that 4 grids, and then we have like pure in vertical, horizontal, all have the same frequency, and put them together, and that's how I get the SST stuff. So we apply that in each month from 14 to 16, from January to December, or all the 36 months. And then in here, I only show you the IMF4 because I think it's more close to the ENSO signal. So you can see at the end of the mid of the 2015, say in July or even in June, we start to have the red signal. The warming signal is coming from Peru, and then slightly propagate to the East Central Pacific, and become like ENSO kind of signal, and then die out at early 16, and almost at the end of the 2016, we can see the blue box, blue color coming out. That's the La Nina year. The La Nina event come out. So somehow IMF4 somehow can represent as the El Nino.
Was 2015?
Some people say yes, some people say no.
It looks like it had to.
Yes. From California, that people they say, but from China, no, we didn't see that. Okay, so this is IMF5, the same things. So you can see each component. This one, IMF5, is more involved with the actual tropical signal. You can see the warming signal from the say like 2015 from the January, it's warming at the extratropical close to the California, and slightly coming down, acting as the seasonal footprinting mechanism, as I think Tony Hurst mentioned last week. Yeah, the footprinting mechanism comes into the equator and form a warming like CP stuff. Yeah, and then die out finish. And then at the end of 16, you can see the cold signal coming down. Yeah, so it's like the so-called footprinting. Also, people also call this is Pacific Meridional mode. So in here we can see IMF5 is more represented as PMM. Okay. To see that is really annoying, really difficult. You can't hardly to see anything. So I give you a animation. I hope this works. Uh-oh. Oh, no, so so maybe I can use the. So, Shifan Dimitri, can you see my screen? I just turn on the YouTube. Yeah, so this is M4. The true, like in space, in time, they share the same frequency. So you can see the El Nino is from the far end side of the screen coming down. And sometimes warming in the center only. So it's more like this is more like a real ENSO rather than previously before they showed different things. And also, I show you in the high frequency one. So if previously a lot of methods we combine all those information together. I don't like it. I want to separate them because all of them are represent the different things. So if you call this ENSO, no way. I don't think this is ENSO. Okay. Come back to the slide.
Check.
Yeah. Oh, okay. Yes. Okay.
So
Yes. Yes, yes, yes. Okay. I just repeat, Harun just asked me if I can see from the ligand lay correlations, if just SST correlate to the Nino 3.4, see if I can see the signal coming from the extratropical to the tropical. Yes. Jing Yu at the 2010 already have that paper. And then that's why, that's the paper I sent to you now. I hope you can help me to review. That's the one I say, the PML actually, that signal, it's only indicator rather than seasonal. Yeah, it's very clear. You can see very clearly. Just, yeah, it's low frequency. Yeah. Yeah. Yes, you can do that. Can. Oh. Yeah. Yeah, you can see that as well. But just like that'll be really noisy. So for me, I just remove a lot of different signal. Yeah. But yeah, thanks.
I can get a correlation of two totally irrelevant time series, okay? Amount of water chicken drinks and the amount of crop production in Australia. I can get a very good correlations, depends by varying the smoothing and lagging. Exactly. Yeah, so I don't know about your field. It's very dodgy with a negative correlation.
So that's why you have to take into the effective degrees of freedom. So if you have very low frequency variability, so for example, you can have 30 years of data, 360 data points, but you can have only say 7 ENSO events. So instead of 360, you'll have an effective degrees of freedom only 7 or 8. So, and that's what you use for, judging your significance of your correlation coefficient. So just because correlation is high doesn't mean that it will be significant. You have to take into consideration how many effective degrees of freedoms are there.
Then I have another problem with any time series. Okay. Again, in my field, we have down variation, seasonal variation, interannual variation. So you can superimpose with diurnal is easy, day, night. Seasonal, autumn, spring, that's easy. Interannual is very tricky because I can superimpose a certain interannual variation. I'll give you an example, ENSO, for example. But this is very arbitrary. So I don't know. I have no idea about your common studies.
We can talk about this later, man.
Yeah.
Okay. Sorry. Okay, so before I going through the rest of that, yeah, Catherine is not in here. Actually, like Yingping just mentioned, and I tried to play Catherine's data. Say we have all the flower in here, and overnight the police come out, and then we have the snapshot of that things. How can we separate that if we just use a time series or something? We can't because it's somehow not correlated. So if you use the EEMD on the multi-dimensions, you can separate the flower and the polyps. Or even by which day, you can figure out. Even Jackie Brown, she talked about the different type of the rice or the different agriculture stuff. I assume we can use this method to decompose it. Say this area is growing the right, yes, anything. Just based on your color, based on the height, or yeah, they can give you some information. Or corn, yeah, I forgot that term. Yeah, corn, yeah, because there's orange color, yellow color, orange color, whatever. So you can just one by one snapshot, you can do this decomposition and figure out what's going on in this area, what's going on in that area. Do we need the water? We have the water shortage or something, or too dry or something? I would assume maybe this is a good approach rather than just the time series only. Or even because sometimes there's no correlation. One night the police come out, yeah, and the previous night there's nothing there. So it's like a snapshot. So that's why sometimes in different fields they have a different issue. So that's why I propose maybe you can try this. Yes.
2D. If I give you a 2D,
yes.
Actually 3D.
Yeah.
In my field again is about vegetation green, how green the surface is.
Yes.
And we would have 30 years data at half by half degrees globally. So with your method, would the ET be able to tell me, at the variability at say every 5 years, how it evolved globally over the last 30 years?
Maybe you can give it a try, because I haven't done that. So yeah, if you can show me the data or something, maybe we can think about how we can do that. Okay, I'll keep going on. So from here until now, you can see even from the YouTube, the video clip I show you. At this stage, the data is still in 3D. We have the SST anomaly. After we separate, decompose it, the data is still in 3D. We cannot plot that animation into the paper because there's no way to plot that things in the paper. So how we can do that? How can we define? So at the end, we still need to use EOF. So that's why in this paper I propose, say, we should use MEMD first to separate the different frequency stuff, and then we apply the EOF on each component, each mode. That'll be give us more physical meaning rather than apply the EOF directly to the SAT anomaly. So I do again, just apply the EOF on each IMF, and we only focus on 3, 4, 5, 6, because I said before, 1, 2 is more noise, and 7 and 8 is like residual, so we don't worry about that. And we just only apply the EOF on the 3, 4, 5, 6, and only choose the first mode. And that will be like the pattern showing here, so we can see this is really like El Nino for the 3 and 4. The 5th is more like a Meridiano mode, and the 6th is already rather really not related to the ENSO, or maybe it's more like a background signal. So if you add up these 4 plots, you got the left-hand side pattern that's really close to what we got before the EOF pattern, but it's much clean as well. It's not no noise, no nothing. And then each EOF we also can have the time series in here. And then as I said before, once you know each component of the ENSO, it's easier maybe for us in the future to do the forecasting, rather than if we use the NEO 3.4, because the NEO 3.4 contains a lot of different frequency, so you don't know your next step should be more contribution from the daily frequency, or from the interannual frequency, or from the decadal frequency. Which one should be dominant that you don't understand? So you only can use linear regression to find. Yes.
So before you applied the EOF, did you add more IMF 3 to 6?
Oh no. It's separate. IMF 3, because each component still in 3 dimensions.
Yeah.
Later on in time. So each component you just apply EOF.
Then
yes.
How did you get that combined EOF? Just adding all the EOF patterns?
Yes, you just add these 4 together. Okay. You can linearly add these 4 together, no problems, nothing. Yeah. Or maybe if you got the EOF first and then decompose the pattern, but I never tried that, so I don't know. Yeah, but from here it's very more clear. 3, 4, 5, 6 do the EOF, and then the combined will be the left-hand side at once. And the other thing I'm emphasizing here, because even Zhao Hua Wu, he's the one to invent this method, he still uses the EOF first and then do the decompositions. But I argue you already mix out the frequency altogether. So how can you decompose your signal? Because you don't know which one you're talking about. So I would suggest do the decomposition first and then do the EOF. So that's the main topic the key point in this paper. So we decompose it, and then also you can see from the power spectrum in here, you can see very clear. We have the interannual, like 2 years peak, and 3, 4 years, and then 7 years, and the last one is more like a decadal signal.
One more question, Arnold. Maybe you talked about it. So you have all these C1, C2, C3 up to C10 or whatever.
Yes.
So when you add them,
yes,
you get the original
signal
time series back.
Yes.
Okay.
Maybe I just quickly show so people who wasn't here last week. So the top is the original signal, and then we can decompose it into, say in this case, the 6 signal plus the residual. If you add up all these together, you back to your original. The So people will confuse, say, oh, this is a linear method. No, 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 no. You add up together, you sum them together, that's linear, but the way you decompose is nonlinear.
Okay, so then why don't you apply EUF first to the raw SST anomaly?
Yes.
So you will get all these EUF spatial patterns and then corresponding time series, PC1, PC2, PC3.
Yes.
And then apply your EEMD,
Yes.
one-dimensional EEMD,
Yeah.
to each of these principal component, and then you'll have another, for PC1 you'll have 5 or 6 or 10 of these IMFs.
Yeah. Okay.
And then, because they are additive, you can take each of these component and then multiply that with your spatial pattern, and then get back the SST anomalies associated with that particular IMF.
Okay. So Harun asked me, just make it simple, why don't I do the EOF first and then do the decomposition? I think at the really beginning of last time, I already showed these things. There's something wrong with EOF. If we have the signal like this, propagate from the north to south,
and just to add to my question, Arnold,
yes.
You will be using EOF not for identifying patterns, but for data reduction, okay? You will be reducing the dimensionality of your data set enormously.
Yeah.
So your UF components will be actually data reduction tool. It doesn't matter if individual pattern gives any physical meaning.
Yes, I know. I know.
So your objective will be to carry out the UF, reduce the dimension of the data, and then to each principal component apply your EEMD.
Yes.
The one-dimensional one.
I know what you mean.
Yeah, and then you can actually get back to that space-time series by transforming back to physical space using the spatial UF pattern.
Yes, but there's one problem in here. Somehow I couldn't show that. I don't know. Yeah. So if we have the signal propagating from north to south, west to the east, east to the west, and then we combine, just add up these two signals together, we will have the left-hand side, that kind of chessboard pattern. This signal we give to the UF to separate the signal, whatever. UF cannot separate that. UF will get another chess pattern like this, and the second mode will be like a half pi, half phase shift, but still in this pattern. Even you can continue to 100, 2000, and the same, it's still the same like this. You can't separate these two. So that's why I will say do the decomposing first rather than do the EOF first, because you want to separate the true signal out, and then from that you do whatever you want to do. Is that clear? Is it
clear? But if you consider the complete set of EOFs, any data can be decomposed, and without sacrificing any UF components, if you transform back using the full set,
yes,
you can recover the original anomalies and original data set.
Yeah, yes.
So,
but you didn't separate, like the point is like you didn't separate the frequency of what I want. So whether it's in interannual signal, seasonal signal, or the decadal signal, you all mix up together, because EOF only consider the maximum covariance or coherence.
Okay, go on.
Okay, Peter, you.
Yeah, I've got a kind of a bunch of questions, but they probably all stem from this basic not understanding. So these different modes in the EEMD, are they each, do they form a set of basis functions in the sense that they're linearly independent and orthogonal?
That's your thinking. In here, we don't have the criteria for the orthogonal. It's this. I don't have an example in here. If you go back and then just have a sine plus cosine, whatever, yeah, because you only have sine and cosine, or sine theta something else. You only have these two signals. So for EEMD, just look at, okay, your sine, your cosine, we just separate you two. But like maybe for other methods, most of the time we'll mix out everything. I got piece of that and piece of that, and then mix out, and then we got something else. You know what I mean? This one is really just separate.
Okay, well, I guess a more fundamental question then, how do you determine the number of modes?
Oh, okay. Yeah, that's very simple. If, like I always say, if you have a box of fruit or veggie, if you have like a banana apple, you just get banana apple out, only 2 modes. If you got a pineapple inside, you got 3 modes. So it's not like you can do 100 times, doesn't matter. You just keep doing, you at the end very small, of course, but it's meaningless. But for EEMD, you only can do certain times until you decompose the signal you have only.
So just to kind of test my understanding of that then, if do each of those modes map onto a particular physical process?
Second?
Can you map each of the modes onto a particular physical process? For example, a Rossby wave in the atmosphere, or given a spatial and time, characteristic spatial and time scale.
Okay. Yeah.
Be mapped onto a particular mode.
Okay. Yeah. Just maybe later. Peter just asked, like, do we have any physical meaning for each mode? The quick answer is no. We don't know what exactly they are. So when Norton Huang invent these methods, they just say like apply in the CT scan. When you do the CT scan, you check your body and you find something next to your stomach which it looks different. It's not your stomach, it's not whatever your other organ. And then the doctor will say, okay, well, let's check what's going on with that. They don't really need the physical meaning. They just find out something which is not in your part, supposed to your body anyway. But for us, we have the big problem. As a climate research, we want to know, like you say, what's the physical meaning for each of them. We need to do that. We need to get, after we decompose it, we need to find the reason. What is that? What does that mean? We do the regression correlation, whatever, try to find the, even just find the like I say, if even we just apply a little, okay, maybe that's in the interseasonal, or the decadal or something else. So we need to other tools to help us. So like EOF, we need something else to help us to know the physical meaning. Just like the first step when we have the EOF, the same. When we have the EOF back to Laurence, when he invented that, there's no physical meaning for each mode. And then after the 60, 70 years, we define the first mode of SST anomaly, that's the ENSO in Pacific. But we still have a question about second mode or third mode. Yeah, so in here, the same. We don't know what is that. So we need to figure out what is that.
I won't sort of continue this line of reasoning because we don't have time. But I just flag where I'm kind of going with this is that there's a new field opening up, obviously, in machine learning at the moment, and particularly around model evaluation.
Yes.
And one of the things that could come out of that is not just some black box, neural network or whatever, which is not very interesting actually, but that they might uncover some basic modes, I guess, or basis functions. I can see that's not mathematically equivalent to an EOF, but that concept where each of the I guess there's a signal, if you like, that maps onto a particular physical process in particular, and that the way this is going, it seems to be a similar, I guess, way of getting at these underlying processes, which might actually also come out of a sparse approach to machine learning. So that's kind of where I'm going with it, but it's very kind of blue sky and I don't really have my head around it. But that's where kind of the questions were coming from. But I don't think we've got time to discuss it, but just context.
Yeah. Okay. Thanks. I'll just keep going. Almost finished. Okay, actually almost finished. Yeah. So based on these two talks, I just try to finish these two papers. and then I will include most of people in here in our group because I will use our model anyway. That's part 1 and part 2. How about the part 3? Yes, there's a part 3. Please come to Dave. Dave will host that section in demos, and then I will show you some results from our model. And then the topic will be, like Peter said, what's the meaning after you decomposing? Say in this case, it's a Westerl wing burst. After decomposing, I just realized, people say Westerl wing burst is sort of like a noise, stochastic forcing something. But after I decompose, I think, and after I try to figure out the physical meaning behind that, and then I think Westerl wing burst maybe it's the signal rather than it's the noise. But the details, please, and what happened to our model simulate the Westerl wing burst, please come to the talk. Thank you. Question?
I think we've had some really good discussion as we've gone along, so thanks everyone for your contributions. Has anyone got other questions that they want to raise with Arnold? Martin looks like he's formulating something.
Can I ask a question?
2 dimension?
We'll go to Siobhan while Martin thinks.
Okay. You said you were going to possibly share the results from our model, but you haven't put them up. So basically, we had the biannual ENSO in there, and you also were at one point trying to find a signal, a sort of why we weren't getting the decadal signal out of California in the model. So I think at one point you did see it, but in certainly one section of the model. I'm not sure which version it was.
Okay, maybe I'll apply that. We still have 2 weeks to work on that. It should be all right.
It's a little bit of a signal there. So was there any evidence of that IMF5 in our model?
IMF in our model?
IMF5 in our model, or was it all down at the IMF3 end of the signal?
No, I didn't check that.
Okay.
Yeah, but I think from the result, maybe you can figure out IMF is something not good in our model.
Yeah, so it doesn't look anything.
Particularly because of the southern ocean warming that somehow destroyed the high pressure system at the south. So that's maybe another reason we got a very frequent and so. But yeah, more detail I'll talk in the Amos.
I'm not going to Amos. Not everyone's going to.
Okay, I'll see you. I'll talk to you tomorrow.
Okay, good.
So I guess I worry that there's an infinite number of ways to decompose anything into modes. I suppose you do your IMF and then you're sort of justifying in a way by comparing your modes to EOF modes. You know, it looks like the ENSO EOF mode. That's sort of a bit hard for me to see exactly what it brings on top of a normal EOF decomposition.
Yes, it's difficult. Yeah, particularly like I say, when I first time show this kind of stuff, people will ask me why you got 3 parallel, or at least 2 parallel El Nino or La Nina. But if you go back to Tony Hurst's paper, use his method rather than recharge and discharge, you can find out he also have this kind of pattern. So like the point is very difficult to compare to the year of what we know already a couple decades. So this is really new. And if this really the mode or something, still need time to figure out.
So, I mean, obviously, you are having hard time selling this because people are asking lots of questions.
That's right. It's good.
Did you try extended EOF analysis? Extended EOF analysis that will give you this kind of time evolution as well. I'm kind of like suggesting all these other methods so that you can find possibly some connections or disconnections with existing methods and what this method actually adds or gives which is not available from other techniques?
Yes. At this stage, from the NCO, I only tried the CEUF and the RUF. Maybe others, maybe I can try to have a look. At this stage, CUF and EUF cannot get what I want. So maybe the one you say, the EEUF, I think maybe I can try. Thanks.
I think EEMD is really was published in 2015 paper in PNAS.
Oh, the real paper?
Yeah.
18,
Wow, the paper PNAS for
1980.
CO2 trends, temperature trends, 2015 is now probably, at least in my field, is taking over EOF. Forget about EOF, EMD first. Particularly for trend analysis and a correlation of two spatial patterns. EMD is the way to go.
Is that PNAS paper, is that a review paper or application?
I think Arnold knows more than I do. In my field, the first application paper I know is using EMD to quantify the temperature trends.
Yes.
Right?
Yes.
Was published in PNAS in 2015 or 2014. I can't remember.
Somehow for us, to the ENSO or climate, we still struggle. People not really.
So why don't you try the ensemble mean global mean temperature? So what people do, they try to use the CMIP5, for example, all the models, and take surface temperature or skin temperature, surface air temperature or surface temperature, and then so they have global mean temperature from each model, and then they average across all the models to get the climate change signal. Okay.
Yes.
So now that is a bit controversial. It has pros and cons and things like that. So I think one application could be of your method could be to that time series. So forget about ENSO. It's kind of multidimensional.
Yes. What's the name? The girl in Med England's group. I think a couple years ago in Cosima meeting, she presented something like that. That time I already suggest her if she can use this. But don't know what's going on after that. That time she already tried to deal with a lot of CME5 SSC trend something. That time already suggest her to maybe she can use EEMD. There's a few paper, very good paper, like a Nature Climate scientific report. Some people start to use this one, but not quite right. So that's why I want to. I didn't argue with them, but I just tell them use the right way to do that. Any questions? Okay.
So yes, some cross-team testing of this sounds like a good plan to me.
For the aerosol team or any other thing, I would suggest to play.
Yeah, bit of a comment on the paper that is to be submitted or almost submitted, or
still in the draft.
That's fine.
I will circle around before I do anything.
And remember, internal review first, please.
And that's why I asked from you the author.
Yeah. So and I think maybe whether it's at our CMIP 6 meeting, a bit of a discussion around authorship on papers. I think it's when we're writing these sort of the core paper that like Dave's putting together. Yes, everyone who's had a hand in the model probably needs to be on that. But I think if you're starting to do some science or some analysis or whatever with the model, then maybe it should be a smaller author list, is my opinion. So maybe, Simon, that we can just put that on for discussion at your next sort of team meeting about some, how we want to go ahead with some of this stuff.
Thanks.
So, yes, let's just thank Arnold for the effort he's put into these 2 seminars to kind of stimulate some thought about methods that we use for our analysis. So thanks, Arnold.
Thank you. Yeah, Zhao Hua and his students. Yeah.
Hi, Siobhan, Mark, Matt, Dimitri.